which is an automated cloud-based workflow for flood monitoring from different sources across the CONUS. Our group, under supervision, Dr. Samadi, we did this work. This is the outline of our today's presentation. In the first part, we will talk about the problem. What is the problem that we are solving using the flood watch? In the second step, we will talk about the research gap. Then we will talk about our proposed workflow and how it is working. And then we will deeply talk about the methodology. And in the last part, we will talk about the research scope and what is the result look like, what is the web interface, and how it is working. The first question here is we have some federal flood data set that is fragmented across different agencies. For example, we have some data sets from the National Weather Service, like real-time gauge observation, or some short-term forecasts, or some flood inundation extent maps from the National Weather Service. And also, we have some data sets from the FEMA National Flood Hazard Layer that has some long-term regulatory flood hazard zone, which is important for us. But the question is how the different data sets are dealing each other and how is they working together, and is there any platform that show all of them together or not? And the gap that we found is there is no link between these different data sets. National Water Service have some data set that for different purposes, and we have also FEMA that it has own data set, and for the end user, they do not should using which of these data set, and it is important to know how we can have a single platform that users see all of them together. Is there any coverage between these different data sets or not? This is the problem statement of our Capstone project. There are many work that have done on this project back to 2013. In the Iowa, Abraham Demir with his colleague provided some work in this area, which was regional web GIS flood damage tools. And to date, we have many work that have done this area. And also, we have some documentation from the federal like GO or Geospatial Data Act that documented this fact that there is no specific single platform that for the flood gather all these data sets together and provide a unique information to the end user. So based on this research gap, we try to create a new platform that gathered all these four different data sets from National Weather Service flood inundation mapping, which provide the river inundation extents, and national water alerts that it is an event-based warning from the National Weather Service, and also National Water Prediction Service gauge, which is a real-time observation from the river, and also the FEMA National Flood Hazard Layer together. And we gathered all these data together, and we created a new single flood inundation mapping for the end user that have access to all these data sets. And this is the core workflow of our work methodology. In the first part, let me visible the pen. Yeah. Okay. We have some input data set from the National Water Service and the FEMA, and also National Water Prediction Service that using the Python processing, we gathered, retrieve all these data and using the SQL database that we developed, created new interactive map that enable to show all these data together. And for this work, we use the Docker container that we created all these source code in a container and pushed in the JetStream for running. And the end user, they will see a web map, interactive map. They have access to different layer of this input data in real time, and it will be automatically updated each 1 hour, and also give the end user some information, statistical information regarding what is the area of the flooded map, what is the severity level, for example, if we use the FEMA map or something like that. And yeah, that's my section. I think, Arman, you should continue.
Okay, thank you, Ehsan. I just sent a request to share my screen.
Okay, should I let me?
Okay, yeah, you should be able to share now.
Yeah, thanks. Okay, so can you see my screen?
Yeah, continue.
Okay, so yeah, as Ehsan mentioned, I think we already just have 5 minutes for Sunil and I. So I'm going to just quickly wrap it up this result part. So as Ehsan mentioned, this is just the online platform for just combining all these data sources to see how would the snapshot of this flood watch interface might look like. This is just a snapshot of it. We already just measured different metrics to show the agreement and reliability of this interface. So I'm going to skip these details of methodology and just show you some results. So as a national view in practice, after just running this FloodWatch interface, this map is just one of the simple results of our work. So you can just easily see, for example, here, this is just the flood event summary, how many flood are occurred at the national scale. And this is also some different information about the FEMA, about the National Weather Service, and about the gauges inside the flooded area. There is also some layer selection by the user that user can even select all of them or some of them based on their need. And also here is just a very summary of the data retrieval for developing this map. So here you can just easily see 100 map features are just showed here, and active flood events are 22 across the nation, and also some more details. So you can also see that there are different flags with different color inside this result. So I'm going to give you more detail about the information that we can gather from each of these flags. So for example, the purple flags just give us the FEMA National Flood Hazard Layer, and you can just see different information. For example, the severity of the flood here and the name of the area, and also the area that might be affected by this hazard layer. And also the orange flag represents the inundation real flood area. And also it shows some detailed information about the name of the event, the area, the severity, and many more information. And the last information that we can take from this red flags are some warning, which is based on the National Weather Service flood warning. And you can just see, for example, this red area might need to receive the warning, and the warning level, for example, would be the urgency is expected. And also there are many more details that can be captured behind the information of these red flags. So this is just a very basic schematic information that we can gather from this online cloud interface. So generally, just the results can give us more than 93, 94% of accuracy and also reliability by using all these three main source of data set for having a national scale flood inundation mapping. So I can just take it to Sunil from one.
Yeah, thank you, Sir Arman. Next slide, please.
Oh,
Um,
okay, I can just share again for you.
We are running out of time, so
Yeah,
I'll
go ahead.
quickly wrap up. Next slide, please. Yeah, our platform Hive hits the 100% refresh rate, and then we have a processing rate is less than 1%, and we have quite large latency, which is about 2.5 hours. And this is gap is between the sub-minute processing and the multi-hour latency that confirms the delay in upstream update from the federal agency and not in our pipeline. Next, please. And these are the real-time evaluation statistics that shows the refresh rate, intersection over union, and other statistical parameters. They are real-time and updated in its refresh rate. Next, please. And the practical takeaway message is that a single source view is incomplete picture, misses the prior majority of cases reported flood signals, and our flood watch provide the multi-source views, complementary sources to keep the visible disagreement surfaces instead of hiding them. Gaze outside every polygon is not an hour earlier, is the signal, possibly the earlier available indicators of the flood event before it is been modeled or formally warned or updated by the federal agencies. And our recommendation is that flood watch can be used as a near real-time complement to the existing signal source tool. It's not an replacement. Surfacing cross source disciplinaries as they emerges. Next, please. And the finally, we develop a reproducible cloud pipeline, and that we hit the 100% refresh rate, and we have 93 to 94% disagreements that the flood gauges locations are not within the flood polygons. And the final takeaway message is that do not merge the dismerging sources, just reveal them. Next, please. And these are the citation and data sources that we use to prepare the presentation. Thanks. And we would like to acknowledge and thank WaterSoftHack 2026 team and leads, as well as the collaborating members. And all the data sources are publicly available in GitHub, Docker, and real-time product link. You can use those links to visualize and have an idea about our products. Thank you. And we are happy to take questions.
Okay, great. So we have 2 minutes for questions. So is there any question from the team?
Yes, I can ask a question.
Yes, Ibrahim.
Thank you. This is a great presentation. So can you tell me more about like what has been done on the cloud side? I mean, because if it's just a data integration system or a visualization system, most of the data could be extracted or ingested on the fly without any cloud backend. So what was the main use case that you used or need the cloud computing? So are you doing any pre-processing or any other recalculating a specific value or other information?
We didn't any recalculated or any normalization because right now they're using the API. All this data is available for end user, and we just gather it. And because we didn't want to change the process of the data that they presented. Just we try to use as input of our pipeline to see and get some statistical information about it, not any flood-related calculation.
Okay. I mean, definitely in this type of large-scale systems, ingesting data beforehand oftentimes helps with the real-time operation because USGS and many other sources may not be serving data in the speed that you want and in that detail that you want. So oftentimes you do that type of pre-processing and pre-ingestion on the cloud just to make sure that the system serves the data in real time, and you can do some pre-processing and new calculations for secondary data as well. But yeah, this is good. Yeah, thank you.
Yeah.
Okay, great. Any question? We can have one more question very quick if there is any.
I have a question.
Yes,
So,
Bijay.
I think there was a big conclusion saying that, 93 to 90% of the flood causes conditions fall outside the official flood polygons, right? So, do you think this massive discrepancy is due to something wrong with the system, or is it just because of a delay in the alert system? Do you have any more thought on this?
I guess it's related to the purpose of developing each of these platform. FEMA, it is a long term that just based on the past information that they have, they selected some areas. But when we compare with the real-time flood extent, most of the time we see that the FEMA is not happened. The polygon that FEMA's forecasted is not happen. Maybe their data is not valid or reliable, but I think this is another research question, that how these data can be gathered together for the end user. But this is the reason that we presented the coverage as a metric to see how these data are have a coverage. And I can also show in the like a demo for you right now to see most of the polygon from the FEMA is not covered with the National Water Service.
Okay, sounds good. Thank you.
Yeah.
Okay, great. So I have a quick question. I will put it in the chat for you guys to answer. So we have to move on to the next presentations. Okay, drought team, you guys are ready? Meg, Ethiopia, Ayubami, and Demi. Can you check and see whether you would be able to share your screen? So you guys have 10 minutes for presentation, 5 minutes for Q&A. Make sure you stick with this because it's important for you to get the point. Okay, so it is 11:23 till 11:43. You guys have time to present your work, and after that, we have 5 minutes for Q&A. 11:48. Please go ahead.
Okay, can everyone hear me?
Yes.
Alrighty. Good morning. My name is Damien, and I worked with Ethiopia, Megana, and Ayobami on our project over edge and hybrid architectures for streamflow drought onset detection, a large sample evaluation across CONUS. To go over what we're going to talk about in this presentation, we're going to start with our background and motivation. We're going to move on to our study area. We're going to divulge into our data and methods, and then we'll talk about our results and discussion, and then end off with our conclusion and a short Q&A. To start with our background, drought propagation refers to a meteorological deficit that moves through the hydrological cycle. This usually presents as a decrease in precipitation that creates a positive feedback loop through runoff, soil moisture, stream flow, and then groundwater, which is the definition of hydrological drought. At each stage, this displays an increasing lag and attenuation, which gets really complicated when you start looking at really large spatial scales. Because of, different areas have different environmental attributes, this can modify the magnitude of this lag and attenuation. Which brings us to the general pipeline of what most literature shows for drought onset detection. It starts within your gauge station, and this is that continuous collection of high volume environmental data, whether it be meteorological or stream flow, that is then transmitted to a central location for analysis. And this is where most of that methodology splits off, where your machine learning algorithms or drought indices and threshold methodologies do the central analysis. After that's done, that's then sent out into drought onset alerts or other products. But in the spirit of this fellowship, what if we incorporated that propagation logic into the sensors to kind of help with this data problem that we've been running into? Which brings us to our problem statement. This existing reliance on that centralized processing in drought monitoring systems can limit the timeliness and efficiency of drought detection, especially so in distributed watershed networks. And what we did to approach this problem was develop two edge-enabled architectures for stream flow drought onset detection. In the process, we created a curated reference database of drought propagation characteristics across 645 near-natural catchments using the CAMELS database. And between these two architectures, we quantified communication and detection performance trade-offs. To talk about our site area, we looked at the entirety of the contiguous United States, which is the spatial scope of the CAMELS database. And we have stream flow and meteorological daily data ranging all the way back from 1980 all the way up to 2024.
Moving on to the methodology section of our analysis, I will start off by looking at the data collection. So as Damien pointed out, we used CAMELS catchments where we collected catchment attributes. We also collected daily meteorological data, more specifically precipitation, and USGS streamflow data for all CAMELS catchments between the period 1980 to 2023. In the data pre-processing stage, we looked at data alignment to see whether or not these three data sets align, and we found that out of the 671, 645 catchments can be used. We also did seasonality tests to evaluate peak precipitation as well as peak stream flow across the CONUS. The data processing step after that utilizes the 1980 to 2004 period of the analysis. So this is sort of the processing step that evaluates the drought analysis. So here we use the variable threshold level method where we use the 30th percentile or the Q70 dependable flow as a threshold to define droughts. Using that, we develop a drought database which has an extensive event catalog showing multiple catchments and multiple drought events within this period. From that, we extract the drought lag, which is the most important mechanism that describes hydrological drought onset. After that, we look at model development, which is the crux of this analysis. The model development focuses on the 2005 to 2023 period, which we call the causal replay. We call that a causal replay because we're essentially emulating the existing USGS gauge networks as if they are a drought onset detection gauge. So we evaluate all three model architectures. We evaluate the cloud, which is essentially the existing USGS monitoring networks. And then we also introduce EDGE, which has an on-device detection algorithm. Here we have two important decision logics applied. The first one is that it uses the existing Q70 thresholds, and then it also uses a persistence window to see if the drought persisted. The second one is the hybrid architecture, which uses the existing decision logic from the edge computing, which are both decision logics, but then it also includes two additional decision logics to do a cloud verification. So that cloud verification step essentially includes an emulated meteorological data that evaluates precipitation deficit prior to the candidate drought. And it also uses the drought lag per catchment as a defining window or a look back window. After this, we did performance evaluation where we evaluated all three models in terms of how well they identify droughts, how well they reduce false alarms, and how well they communicate. And then lastly, we also did a sensitivity analysis on the hybrid architecture to evaluate how a persistence window change would influence how droughts are detected, as well as how varying thresholds contribute. Next slide, please. So to show you a brief overview of what the event catalog looks like, at the bottom you see multiple HRUs with their own start and end event dates. So this is essentially developed for all catchments in the CAMELS catchments that we identified, as well as all events within the training window. At the top, you see a sample data, which is essentially showing you one row. At the top, you see a meteorological drought, and second panel shows a hydrological drought. The red area indicates that drought deficit. And the important term here is the lag, which is the delay between the meteorological drought start date and what we're trying to predict, which is the hydrological onset. The Q70 threshold is again another important term here, which is applied for both the EDGE and the hybrid detection algorithm. And all of the drought events are validated against NIDIS drought data. Next slide. And just to show you a brief overview of what that lag component looks like, over the entire United States, we see that lag generally increases from arid and humid rainfall-dominated areas into snow-dominated areas, where you can see in the mountainous upper Colorado and Rio Grande river basins that there is a much larger lag compared to the southeast portions, which are highly humid and highly responsive. And we use this lag as a physical property to set the cloud verification window that will be described later. Next.
These are the results. So before we trust either architecture across the 645 basins nationwide, we wanted to do some sanity checks. So the figure, it shows the catalog, which is the ground truth, and the edge onsets declared and the hybrids confirmed. And we found that edge over declared, which is 25, 40, 36 on it, onsets versus the catalog's 4, 5, 7. And also the hybrids confirmed counts were 4, 5, 6 looks close to the catalog. And as you can see, for this basin, there are 5 confirmations, 5 catalog events, only 1 corrected and 4 false. This was only for the 3 basins, and the counts, what we have the counts doesn't necessarily should match the dates. So we needed metrics at a larger scale, which is 645 basins. So this is the detection performance across the 645 basins. As you can see the figure, it is the distribution of POD, FAR, and CSI for hedge and hybrid across all the basins. So as we see, the hybrid cuts FAR sharply from 84% to 60%. Verification rejects real false alarms, but the POD drops even more from 37 to 10%. It also rejects real events. And also we saw that comparison of the edge and hybrid beats edge on CSI in only 243 of 645 basins. So fewer false alarms, but not very accurate. So this was for the 645 basins. So the question we asked was, of those 38% basins where the hybrid is performing, is it random? Scattered evenly across the country, or is there a pattern to where the hybrid wins? Next slide, please. So this was the scatter plot. So what we found was the hybrid wins in patches, but not broadly. So each point here is one of the 645 scored basins. The hybrid performs identically to the edge. Majority of points, they fall below the diagonal, that is, edge wins in most basins. So it's very clear that low to moderate edge CSI basins, they sit clearly above the diagonal. So this is a pattern, not a noise. Hybrid doesn't precisely do best where edge alone struggles. So could this be tied to something physical about those basins, or it just a random variation in the data? So the next question we wanted to ask was, what do these basins have in common? So what we did was we split the basins by region specifically, especially we took HUC 14, which is the Upper Colorado, which has the longest lag, and it is the most snow-melt dominated region in the study, with a median lag of approximately 40 days. And what we saw was, this is edge and this is hybrid. So inside HUC 14, the hybrid's mean CSY was 20%, clearly exceeds edge of 0.1 to 1. That was a 65% relative gain. So leaving this HUC4 in the 628, the rest of the corners region, the pattern reverses. Edge wins on 63% of the basins. And the next thing was, we wanted to check the communication and the energy efficiency, and we found that both edge designs cut the transmission independent of accuracy. So we found that per basin, median reduction factor was 36.9 times fold for the edge and 130.8 times for the hybrid. So the first figure is the aggregate message cost. The second is the per basin reduction across all 645 basins. And then we show the estimated battery life versus per basin battery life across all 645 basins. So we found that this efficiency gain holds uniformly across all the basins, regardless of whether a basin fell into hybrid's 1-hour losses accuracy region. And also the message cost benefit of edge computation is robust. It is independent property of the architecture, while the accuracy benefit hybrid's cloud verification is not. And then we wanted to see if we can push the detection accuracy up. So we did a sensitivity analysis. We tested two design choices, the persistence window and the streamflow threshold. So the question we asked for the persistence window was, does hybrid really need Edge's 30-day persistence check, or could the device raise candidates sooner and let the cloud clean it up? So these are the results. The first figure shows the persistence window sensitivity of hybrid CSI versus the hybrid on device. So we varied it from 1 day to 30 days, and we found that CSI collapses from 0.11 to down to 0.031. That was 72% relative decrease. And also device still confirms roughly the same number of candidates. They're just wrong more often. So what we found was the persistence and cloud verification aren't interchangeable. And also the second test we did was the varying the streamflow threshold from Q60 to Q70, which is the current one, and Q80. So the question we asked was, what if we just define drought more strictly? So the Q80 instead of Q70. So we saw that the CSI roughly doubles from 0.11 to 0.222. The POD also increases, which was 98% relative increase. FAR falls in the step not traded off, and there was 14% increase in the message count. Next slide, please.
You guys have 1 minute. Can you wrap up quickly, please?
Yes. This was the POD, FAR, and CSI distribution under all the thresholds, streamflow thresholds, Q60, 70, and 80. And we found that FAR and POD, but FAR falls monotonically, but the POD rises. The next slide, please.
For the conclusion, both the edge design and transmission perform relatively better compared to the cloud streaming, and the verification advantage is notable in the long lag, and the snow melt catchment with a 76% improvement. Verification trade also is a detection for fewer false alarms, and a user deficit threshold raise PO and lower the FAR, indicating threshold sensitivity to drought detection. Next slide. So the application and transferability, these projects can be transferred to tailors per site using lab values, since they each site have different lab values and hydrological data. Also, the transferable to gauge catchment is also possible, as I earlier mentioned, because of the different lag threshold, and also this whole setup is very efficient for false alarm reduction. Next slide, please. For the future improvements, additional predictions such as the soil moisture and groundwater and other variables can also be added to make it more robust, and also where higher detection is required, a more robust machine learning could be used, such as the gradient boosting, and also a probabilistic verification could be used instead of a 1 or 0 system or idea that we implemented. Next slide. Yeah, so we'd like to acknowledge the WaterSoftHack team, our PI, Dr. Vidya and Dr. Bichaya, and also thanks to Kwasi for the improvement in the WaterSoftHack program. Thank you so much. Yeah, these are reference, and thank you. I'm very happy to receive any questions. Thank you.
Yes, great. So we have 2 minutes for questions, 2-3 minutes maybe. Is there any question for this team? So you guys mentioned that you found a lag in the West Coast, in the mountain region. Could you elaborate more on that portion? It is really interesting. And also the value you provided for cloud and hybrid model, which could be more efficient in handling with your modeling work. So how you come up with that number? Could you provide more, elaborated more, please?
Yes, I can answer the first question. The first question deals with the black component that varies across the CONUS. So here we found that the snow-dominated landscapes had a much larger lag a median lag of around 40, ranging up to 70 days. This reflected the fact that these areas waited for snowmelt to contribute to the hydrology of that river basin, and therefore that increased lag that we saw is essentially the system converting from a meteorological anomaly into a hydrological anomaly, and that was directly driven by snowmelt conditions. So for that reason, we found that there was a much larger lag compared to the southeastern portions, which are more directly responding, and that's essentially looking at a larger lag across the Western Highlands compared to the other ones.
Great.
I can answer the second question. It was about the performance metrics for the edge and the hybrid.
Yeah.
So what we did was like we did two verification metrics. One was the probability of detection, the false alarm ratio, and the critical success index. So a true catalog event was counted as a hit if at least one predicted onset fell inside the start and end date of the event. So what we did was like there was two logics for the edge computing, and whereas when it came to the hybrid, there was also a verification logic in the cloud. So where we took the independent precipitation into account and looked at it with also in relation to what we had with the edge.
Okay. Okay, great. So do you know how many credits you guys used in the cloud computing overall?
I don't think we checked. Meg, did we check the credits?
Yeah.
No.
Yeah, that's okay. No problem. Okay, great. Good job, drought team. Okay. If you guys have any question, you can ask this team. You can enter your question in chat, and they would be able to answer it. So let's move on to the next team. Our next presenters are Hydrogeo Chem Explorer Group. You guys are ready? Okay. Let's start at 11:43. Last time I was a little off to 11:53. You have 10 minutes time. You can get started at 11:43 sharp. Elena and your team.
Yeah, okay. Do you see the screen?
Yes.
Okay.
So I
Awesome.
think that would be great if one person share and other people can actually,
We see your second screen.
Oh, yeah, that's true. Thank you. Let me reshare. Now better?
Oh, yeah.
Okay.
Let me
Yes.
know when you start.
Okay, you guys can go ahead.
All right. Good morning, everyone. My name is Bali, and I'm here to present our work. And other folks on this team includes Ryan, Morale, and Galina, and also our WaterSoftHack advisor, which is Dr. Samadi. And our project is titled Learning Groundwater Chemistry, basically built on a transformer-based prediction of mineral saturation indices. Basically, what we did was just to teach a model to predict whether groundwater would dissolve or deposit minerals using the only available chemistry that the USGS provide to us. Here is our roadmap for today's presentation. Next slide. So basically, as water moves through the rock, it reacts with the minerals that it touches, and this can either dissolve some of them or basically deposit the mineral. And this basically explains what the saturation index means. This is a number that captures all these events, and it tells us whether a mineral such as calcite, gypsum, or silica is about to precipitate or dissolve. And that one number, which is the SI number, drives this very outcome. And this also includes pipe scaling, corrosion and the release of metals like lead. Now, there are two ways to get this number, and each of it comes with a caveat. The first one, which is FRIXI, and this is the gold standard geochemical model. It is accurate because it runs the full thermodynamic specification, but it needs a complete water analysis dataset, most especially alkalinity, plus the rate computation. So this is not practical for a quick decision in the field. The second option, which is the empirical formula, such as the one derived by Benevente et al. Now, this gives you a fast field-ready estimate just from conductivity, pH, and temperature, but they are calibrated over narrow ranges, and they cannot capture the non-linear interaction between ions and minerals. So we're left with choosing between accurate but slow and fast but limited. Next slide, please. That gap is exactly our problem. Now, everyone depends on water, whether a utility, a regulator, or a homeowner. Everyone is really asking the question, will this water scale up and clog my pipes, or will it corrode them and leach toxic metals like lead by the time it reaches the tap? Now, saturation index that we've used in this project answers that question. But computing them properly needs full specification and complete analysis. And also, we require a large set of data which are often missing. Now, public records are sparse, with most the important parameter needed for this simulation are missing, and many aquifers have only a handful of samples. So our goal is to build a physically constrained machine learning framework that predicts saturation indices directly from the data that we can get, which includes the major ion chemistry and how it works. What we did was to do this across different aquifer types around the country. Next slide. Now, here's the core of how we did it, and it comes down to one idea: train a large set of data set in cloud and deploy a small one at the edge part. Now, on the right side, we have the cloud, which is the teacher. We use the TAB PFN, a tabular foundation model running on GPU. We train across a large pool data set spanning many aquifers. And we optimize purely for accuracy at scale. Now, that model then emits what we call soft labels, which is its own prediction to teach a smaller model. And that's on the right, which is the edge. We call that the student. Basically, it's a compact, light GBM model exported onto Onyx. Now, these are only run on CPU only, just 10 kilobytes with sub-millisecond latency. Now, they run fully offline on a gateway or in a field logger. Now, so it's the same capability in two footprints. The heavy accurate model where you have the resources and a tiny fast surrogate wherever you actually need the answer. Next slide.
So our Capstone objective was to build a machine learning model that can reliably predict mineral saturation indices even when the available water quality data are incomplete. This is important because many historical datasets from government agencies are missing key parameters. And modern smart sensors often measure only a limited set of ions. Next slide, please. Next slide. This is our whole workflow. We began by compiling a national scale groundwater chemistry datasets from major US aquifers. To address a sparse sampling, we expanded using a Gaussian Kukla generator. Next, we run FRIXI on the synthetic chemistry to compute saturation indices, giving us a large consistent training set. Using this, we train a transformer-based tabular model, TAB PFN. And finally, we test the model with different number of input parameters to evaluate how prediction accuracy changes as chemical information becomes limited. Next slide, please.
So we compiled a national scale groundwater geochemistry dataset, and we decided not to focus on one aquifer because we want our model to be able to predict and calculate saturation indices for different types of conditions. Like my colleague said before, if some data is missing or you pick a new area, then our model is trained well to still get an accurate result on saturation indices. So that's why we didn't limit ourselves to one specific region. We consider 16 principal United States aquifer systems that are located in different parts of the country and associated with different base ground rock conditions. So we have carbonate rock aquifers, we have basin fill alluvial aquifers, and we have basaltic rock and coastal plains. So we take into account carbonate conditions, maybe some saline conditions, and different types of minerals in geochemistry, underlying geochemistry for those aquifers. But as my colleagues mentioned, the data that come from USGS usually is pretty sparse in time and space. So if you remember the previous map, so those locations will be kind of clumped together in a few different, more densely populated areas, densely sampled areas. So to be able to overcome that, because we want, again, our model to be able to work with different types of data, we did create a larger synthetic data set using Gaussian cupola combined with Latin hypercube sampling. So what it allows us to do is to build a bigger 472,000 observations synthetic samples based on just 10,000 real analysis.
Hello everybody. Hello everybody, I am Ryan. So we are going to discuss modeling technique in water quality. So as we see the FRIXI, that is a physical based model that is depend on the physical hydrological equation. The second is the semi-mechanist model that use like empirical and static relationship. And now the model we use PFN, which is a transformer based foundation model, is of course a data driven model. Next slide. So why do we need data-driven modeling? So as we see, there's a number of limitations in physical and statistical modeling as it depend on the domain knowledge and hydrological equation. So for every area we have to run it again, run the simulation again, and every simulation take minute to hour, and it does not generalize from one aquifer to another or from one basin to another. So there is a need of data-driven modeling. Next slide. Yeah. So how does the evolution of data-driven modeling? So from classical machine learning to foundation model, there is a like evolution from 2000 early 2000 to 2026. So first classical machine learning model came, which is random forest, linear regression, and then deep learning model like LSTM, CNN, GNN, hybrid modeling, and transformers. After transformer came like in 2020. After that, after 2023, there is a rise in foundation model. Like foundation model is a pre-trained model using a transformer architecture on the millions of data, and you can use for your problem using in context learning. Next slide. So we use TAB PFN, which is a tabular-based foundation model, as our data was synthetic, which is not a time series. So we use TAB PFN, which can work on tabular data point form of data using in context learning for classification and regression task. In our case, it was a regression task. So we run the model on different grouping of variables with full chemistry, which carbonates, which major anions, and to see the result, how it is related to our output variable using different groupings. And we get a result with different grouping like full chemistry. We get the obviously the most good result with full chemistry with carbonate system. We get the good result for few of the output variables that were directly related to carbonate system. So in this way, we did different ablation study to justify our results. Next slide. So our model performance with different grouping like complete input major ion carbonate system, and you can see the results how for calcite, dolomite, magnesite carbonate system input can work well, and in the same way for silicon metals, quartz, and other output variables is doing good. So in this way, we justified our results and did ablation studies. So this is the comparison of the TAB PFN model using different grouping input variables.
Let me wrap up with the main conclusions. Our results show that machine learning models can successfully learn the geochemical relationship that FRIXC computes. We also quantified how accuracy declines as chemical inputs are removed, which helps define the minimum data needed for reliable predictions. The model performs best with full chemistry, but it still maintains a strong accuracy for carbonate mineral saturation using only core carbonate system variables, important for understanding hardness and scaling. Overall, the model is not a replacement for FRIXC, but it serves as a fast screening tool for processing large datasets. Looking ahead, using electrical conductivity (EC) as an additional indicator for missing ions could make the approach more practical for real monitoring networks. And extending this framework to time series forecasting could help detect early changes in mineral saturation, scaling potential, or corrosion risk. Again, we thank WaterSoftHack team and Quasi for training support and project supervision.
Great. Any questions we have?
Yes, excuse me, I have a question.
Yes, Arman, go ahead.
So yeah, on slide 17, I guess you showed some scatter plots. Yeah, so is this the result of training or validation?
So it's the result of like testing.
Okay, so it's
Yeah.
your validation. Okay,
Yeah.
so for the testing, so you can just visually see that R square is roughly 1 for
Yeah.
all of these 4. So
Yeah.
isn't it sort of overtraining the model? How can you just describe this?
Okay. Yeah. So I can when I got this result, so for the input variable and the output variable, there is a very direct relation using the equations that FRIXC using. And you know that ML models can get this mathematical relation very fast. And so the input variable and the output variable were directly related or linked with each other using equation that FRIXC is using. So it gave perfectly near scores. So we did other ablation studies to see what's the effect of input variable to output variable. If you see the next slide, like the heat map, yeah, here you can see that if for the complete variable, the score is perfect because the input and output variable are directly linked using the mathematical equation. And that's why FRIXC, so there is no hard task to do that because they are mathematical equation. But if we see major ion and carbonate system using a fewer input variable to predict all the variables, then you can see the result changes and telling us the relationship between input and output variable. And our goal was that if the full variable isn't available, like the FRIXC framework need, how can we predict the output variable with less number of input variable across aquifer? And the second thing is that in our proposed methodology, how can we transfer our knowledge from one aquifer to another? Because it will be a generalizable framework for predicting these saturation indices.
Yeah, exactly. So as you mentioned, either if it's an mathematical equation or black box model, whatever, so it means that the model is just producing the input again. So this heat map is really excellent, but I would just suggest that maybe you can use the heat map to show the correlation between the inputs, not just between the input and the output. So if you have multiple inputs, you can just easily see that, okay, which one might be more important for the model output. And the last question as a follow-up, does this tap FN a physically constrained input to your ML method or not?
Can you repeat this question again of
Yeah,
tap PFN? Okay.
yeah. The tap FN, does this tap FN make your model physically constrained or not?
So all the ML models are not physically constrained because they depend on the data. They are not running on causal relationship. They are running on the like on the getting the relationship from the weights during the training. So these are not physically consistent models. All the ML model, all the deep learning models, that's the problem of deep learning model, but they are giving good result to us in literature. So we do ablation study to see that if these model are physically consistent or not.
I want to add that when we made a synthetic data set, we did a sanity check and we included some constraint, geochemical constraint for the data set already. So it's synthetic, but it can happen in the real world because we changed we checked the charge balance error. We did some other, incorporate some other like hydrochemical patches constraint there. So the data sounds reasonable.
Okay, great.
Thank you.
So we can have one more quick question, if any. Great. So can you briefly, guys, explain how synthetic data affected your result? I know you said you don't have enough data set to build this model and you have to do that. I also see you have some minus value in your performances. So is it as part of the synthetic data or how you can justify that here?
So like the minus value in the results, like silica and metals in that grouping, there are minus values. So these minus values showing that when we are taking the input group of silica and metals, so the gypsum and anhydrate are not directly related to that input feature. That's why the result with that input feature is not good. So we can see that there is no direct relation between silica and metals. So that this ablation study is doing. So we divided our input into different group after running on the complete input to see the relation. That's what the minus values is representing at this point. And we had a real data that was sparse, and the Frixie framework need data that should be continuous, that having the proper values. So that's why we have to make a synthetic convert our data into synthetic and then feed to Frixie and get the saturation indices.
Okay,
Yeah,
great.
so our model does a good job on the data, and the negative values are not because the data is bad, is because it's kind of was expected a little bit, since you only take part of ions that were measured to predict something that chemically is not really related. So that's why Frixie wouldn't be a good fit for that, because it wouldn't be able to do all chemical reactions and calculations behind the scenes. But our aim was that our model will be able to, with some grain of salt, but we'll be able to predict how those minerals will, well, if they will be precipitating or not in this environment, even though we don't have the major ions that Frixie would have used for this computation.
Okay. Okay, great. Great. So those are not the, weak performers or.
No.
So I thought maybe, okay, that's the correlation then. Okay, great. So.
Thank you.
Okay, great job. Next group is LSTM flood forecasting team. So you guys are
Yes.
ready?
Yeah, just give me.
Can you check your screen and see if you would be able to share. You can start at 12:05 and then you have till 12:15 to present and 5 minutes for Q&A.
Okay, so do you see my screen? Does everyone see my screen?
Yeah, great.
Yes,
Okay.
you guys are ready? Then okay.
Yes,
Good.
let's go.
Okay, good morning, everyone, and thank you for the great presentation. Today, my team and I will present a project on enhancing operation flood forecasting in semi-arid basins with data-driven models. So my team is Omid, Amir, Francisco, me, Hassan, and Jenna. So we will give you introduction and background, research questions, the study area and the methods, the results and discussion, conclusions, and the acknowledgement at the end. So, okay.
Yeah, go ahead. Sorry, I
So
missed.
in this picture, this picture is not foreign to you. We have seen this many times in the news and probably part of your research. So flooding is among the most widespread natural hazards. And since the early 2000s, global occurrences have increased 4 times across tropical regions and almost 3 times in the northern mid-latitudes. And with this, there is a great cost, almost $850 billion in damages nationwide in the US, and thousands of people lost their lives. So what we can do about this, Omid, please back.
Yes.
Okay, so the national water model have been, I think, since 2015, the Congress provided resources to the Office of Weather Prediction to develop an advanced continental scale forecasting capability, and the national water model had been an important tool for flood hazard management. So it provides forecasts for over 2.7 million reaches across the US. But the problem is that the national water model is not performing very well everywhere. Next. So in a study done in 2023, evaluating the national water model using the normalized NSE, where every point less than 0.5, so every point here is a catchment, and this is in more than 4,000 catchments. Every point less than 0.5 means that the model is not able to predict better than the mean. And whether in natural or controlled basins, you can see that there is a pattern emerges in this map. The one on the left, the right part of the US is have a good performance, but the left part where is more evapotranspiration and the aridity, the performance is pretty poor, and there is room for improvement. Also in the figure below, just 1 second. Okay, so yeah. So what we can do about this with the room of improvement, machine learning have been used the first time, deep learning models, especially LSTM in 2018 by this paper showing the improvement or the simulation of the hydrograph using LSTM for rainfall runoff modeling. And with epochs, you can see the improvement in the simulation. In the figure in the left, in the right, sorry, is showing when static attributes were even introduced to the model, there were even better performance or improvement in the simulation in most of the basins. So each point here represent one catchment, and all the points below the line showing where there have been improvement when the static attributes have been introduced. So Jenna's gonna take it from here.
So these issues with the national water model, and then also the potential for machine learning to help with these led us to the following research question that how can LSTMs be used to improve streamflow forecasts performance at the regional scale? And with that, we have 2 main objectives with this project to develop a regionally trained LSTM model for the Nueces River Basin in South Texas, and then evaluate this model relative to USGS observations and also against the national water model, the short-term forecast. And our study area, we chose the Nueces River Basin in South Texas, which originates in the Edwards Plateau and then flows approximately 350 miles southeast before discharging into the Gulf of Mexico. So this watershed is defined by semi-arid conditions with large variability in precipitation. So it'll have very dry conditions for part of the year and then random very intense rainfall, resulting in flash flooding conditions, which can be very difficult for the national water model to forecast correctly.
Thank you, Jenna. So one of the reasons why we picked this specific study area, when we take a look on the National Water Prediction Service map for US, by the time we have this hackathon session this previous year, we found this previous week, sorry, and this week, we found out that this area in Southeast Texas and South Texas have major flooding conditions. So the water surface elevation for most of the river exceed the AHAB's major flooding thresholds for most of the gauges. So you can see in the upper right figure how were the flooding conditions by last night for the Nueces River near Three River Station, and how are the flooding conditions in the upstream gauge of this location. We can see here that these flooding conditions have been happening since last week, so that's an ongoing flooding, major flooding happening in this region. So that's why we decide to keep this study area to be more try to be more realistic with current flooding conditions. In terms of the data that we use, we provide the LSTM model with USGS data. All of this data was pulled from the USGS API source. So this all this data could be accessed basically near real time. All this data is generated every 15 minutes. We resample all the data to 1 hour for the training task, keeping the maximum value of each hour. We try to we delete duplicate readings by making average if we have those within the record, and also missing data field with linear interpolation for all the 8 years of data that we have available. So we split these 8 years within 3 time windows: training, testing, and validation for all the training LSTM section. And for actually comparing the results, so we have National Water Model Short Range Forecast. All of this data was pulled from the Amazon Web Bucket service as a comparison, where all the forecasts extracted were selected for the nearest reach close to the USGS gauge. And all this stream flow data was also converted to gauge height based on rating curves. All of this data was also published by USGS, and we were available to pull all this data directly from the web services.
So thank you, Francisco. For the LSTM forecasting model, I used the stack LSTM architecture. The model takes the previous 168 hours or 7 days. The 7 days because we want to add the physical meaning to our model. So because the lag time was 4 days, and we choose to use the 7 days here. So we use the hourly gauge height, as the Francisco mentioned, from the target gauge and the upstream or donor gauges. And from those 7-day history, it predicts the next 18 hours of gauge height simultaneously. This is important because it's direct multi-horizon forecast, and all the 18 hours are predicting in one step forward. So architecturally, I used a 2 LSTM layer with 96 and 48 hidden units, followed by 40 unit dense layer, and an 80 unit output layer. We add and dropout to generalize the model well, and we use the cross with TensorFlow. So next slide, please. For training, we use the Adam optimizer and Huber loss. We use the Huber loss because it's less sensitive to extreme spikes, while it's allowing the model to learn the flood behavior. So here the red curve is training loss, and the black curve is just the validation loss. Training loss continue to decrease, while the validation loss reached its minimum on epoch 8. So after the epoch 8, validation performance no longer improve, and we use the early stopping procedures to store the model weights from the epoch 8. So next slide, please. In this slide, this figure shows the performance across full 18 hours forecast horizon. As expected, forecast uncertainty increase as we increase the lead time. Both MAE and RMSE generally increase as we move forward further into the future, and the NSE will gradually decrease. At a short lead time, 1 or 2 hours, the RMSE is around 0.2 to 0.25 feet. and by 18 hours, it increased to approximately 0.8 feet. However, the NSE remains around 0.75 even at 18 hours lead time. Overall, the main result in the LSTM will present with Ami.
Okay, so from now on, for the next 3 slides, we'll focus on some case studies. So this is a flood event in October 2013, and this is the most extreme flood event that Gage has experienced. So we used the target gauge is shown at the bottom row, and we used the top 2 rows to predict the bottom row. And you can see that we can accurately follow the rising limb and the falling limb of the hydrograph. Also, we are slightly underestimating the extremes. And this is the second most intense event in August 2022. Again, the same setting, and this time we are following the hydrograph of the observed stream flow even better. And this is the near real-time comparison. So the event that is going on right now, and that was the reason that brought us to this case study. So you can see that, and here we are also having the National Weather Model short-range forecast as well. So you can see that we are accurately following the rising limb of the hydrograph. Also, we are slightly underestimating the peaks of the flood that is happening, but it's in a good shape. So for the conclusions, we can say that the LSTM Nash South clearance from 0.83 to 0.75 across to 1 to 18-hour lead times, and it works better. It outperforms National Weather Model short range in other studies, which was reported as -2. We demonstrated that the model captures the dynamics across several past flood events. Also, it underpredicts the flood conditions for the current ongoing flood event. And future works including additional basin characteristics and also forcings, which allow us to apply this method to other ungauged basins as well. And another good thing, one thing that we really love about this project is that we uploaded all the codes on the WaterSoftHack GitHub, and everyone can exactly reproduce what we have done and shown in these slides. And that's it. We're happy to take any questions.
Great. So we have 2 minutes for any question you guys may have.
Hello,
Any
I have a
question?
question.
Yes,
Thank you for your interesting work. I have a question about the architecture of the cloud part. In the 3rd year of the WaterSoftHack, we should develop a flat workflow that running in real time. And I wanted to know, for example, this machine learning model that you use, each time that retrieve the new data is retrained or not in the long term. Do you have any retraining or not? Can you explain it?
No, it shouldn't. So the results that I just showed you, so we didn't train the model again. We just used the already trained model to predict, at least, say, in so-called real time. It's not exactly real time because it's not like automatic. We haven't programmed it yet in a way that it retrieves the data online and in real time and predicts. But this results shows a very similar case study.
I'm curious about to know what is the dispatch process that you consider for your workflow, and what is happening in your cloud when you run this on your local or cloud server.
To answer your question, we just train the model on cloud, and we just gather the data on cloud and just use the pre-trained model. We don't train the model on real time, so we just use the pre-trained model, and it just super fast, maybe 20 seconds we can got the answer, and these results show the near real time that we use the pre-train. So we just use the cloud for getting the data and run the model on that. We don't retrain the model.
Yeah.
Okay, I got my question. Thanks.
Great. Any other question you guys may have? Okay, great. So you guys, NSC varies between 80% to 75%? 83. I mean 75 to 83%. Okay, is it the
over the test period? Yeah.
Yeah,
Sorry,
it
go
is
ahead.
test. Okay, not validation. Sorry, training. Okay. Okay, and then how big is your basin? Is it
It's very big. I don't have that on top of my mind. Maybe I can say 15,000 square miles.
okay?
Usually.
Okay, great. So you have 3 USGS gauging station there.
We selected these 3, so the flood is happening over
Yeah.
it's already been happening, but we use the red ones to predict the green one
Yeah.
18 hour ahead.
Okay, and then how was the data quality, in terms of gap in the data set? I know how data can be sometimes tricky to have all, complete kind of blocks of data.
We had the
Yeah.
data available around 93% for each gauges. So we put, I think, the data availability in our
It is in the report. In the report, we have
position.
we have the total amount of data, the percentage missing. One of the issues of this particular watershed, basin overall, is that we have basically zero flow, as we have an arid place. So it's basically zero flow, and we start to have reports of water surface elevation as we have these precipitation events over the domain. So it's a quite particular basin to study, and the gauge that we are using is called Three Rivers because is downstream the confluence of Three Rivers. So we found that this is the main river, but obviously the impact of the other 2 rivers could be also a thing to analyze later, right? So this is a quite challenging basin to analyze.
Okay, great. Okay, great. Seems to be a challenging kind of.
Yeah, because we only focus on this branch, and then we have another branch here which is controlled by a lake, but also this branch is also important. Like that's at least if I want to do one more thing later is that we will bring one more gauge from this branch as well.
Yeah. Okay. Wonderful. Great. Okay. So I think we are done with your guys' presentation, and thank you to all of our fellows for the excellent Capstone project presentation. So your project that today you present reflect not only your technical skills, but your ability to think differently and think innovatively about the water science research and how you can use advanced cyber infrastructure and technology to create solution to manage water system. I would also like to sincerely thank you, our instructor, Dr. Bijay and Mihail, and our team and partner, and all WaterSoftHack participants in week 1, and also you guys in week 2, or fellows, for your support, your enthusiasm, and your hard work through our program. And congratulations again to all of you for impressive work and achievement you showed today. So we see you guys at 2 p.m. with our final session and or ceremony and announcing the winning team. So please come back at 2 p.m. Eastern time.
Can I ask a
Thank
short
you.
question?
Yes.
Have our instances been already like shelved or deleted, or do we have some time to copy the data?
Yes.
Yeah. No, they're still running, so you should be able to.
Okay, awesome. Thank you.
Yeah, I think we can keep it running for next 2 weeks, unless, we have to shut it down and then we'll let you know.
Thank you so much.
Thank you. So WaterSoftHack team, the PI, could you guys stay? The closing ceremony sessions. So thank you again for joining us. Vijaya, please.
Thank you, everybody. Thank you, all the PIs for their, effort in, starting in, I think, early February, right, for making this seminar possible. Thank you to all the fellows for, joining. I hope, you had fun, right? Learning about some basics of cloud and edge computing. I hope we are able to, demonstrate that these technologies can be useful for different water science applications, right? And as your projects show, clearly, you have, gotten introduced with these topics well. So, for clouds, if you recall, right, we started from the basics, right? And we saw, how the elasticity helps, right? How, on-demand computation helps, right? And, when to deploy, what are the things that you have to be careful about, and so on. For edges also, right, we saw how, when edge computing is critical, right? How it can, keep things going even when communications networks fail, and, when catastrophes happen, right? And finally, when we saw the hybrid system, we saw that, edges can act as, distributed eyes in a sense, right? So which can sense a lot of different things. And based on, how things flow, we can, do some smart computation and aggregate things that can, provide us with valuable lead time, right? In, forecasting catastrophic events. So, overall, I hope, you can, build further on these technologies, right? And use them in your research, which I hope, will get to see in, leading journals and presentations. So I also want to, remind you that the fellows will receive stipend from Clemson, and I think Dr. Vidya will follow up on that. I think Clemson will need some information from you, and once you provide that, I think each fellow will receive a stipend of $1,000, and we are very thankful to NSF for, making this possible. Right? I mean, you have spent 2 weeks of your time. $1,000 is not much. We all agree, right? But still, it's something, and we are very thankful to NSF for making this happen. On top of that, right? So thank you all for, the amazing projects that you shared, right? So, you were able to accomplish so much in essentially a week's time, right? You were able to form the team. You were able to, formulate the problem, and then you were able to, learn how to use Jetstream, right? Which is different than, just understanding the concept of the clouds and edges, right? So this was, very impressive. And thanks for, the wonderful presentation this morning, and submitting your uh, uh, paper, right? Position paper, which was, mostly well formed, right? And I think great to see, right? Essentially, that you have this completed project, which is, ready for presentation and submission. This was great. So, as we all said, at the beginning of the seminar, we'll, judge the teams, and present a single award based on, how well the project is done, right? And how well the project is executed in a sense. So let me tell you a little bit about the judgment process. So once we got your presentations and the papers this morning, right, we sat through your presentations, which were all amazing, right? And so all four teams were like evaluated by six independent judges, right? And like, the scorings were independent. And like you were judged on problem motivation, right? The position paper, right? The content of the paper, right? The write-up and so on. The presentation itself, right? That you gave this morning, and how well the project was executed, right? And once all the six judges evaluated on these four metrics, right, through scales 1 through 4, we aggregated them, right, and then looked at the overall scoring. And I have to say that this whole process was for at least for me was a bit challenging, because I thought you all did exceptionally well, right? And even the final scores kind of seemed that things were very competitive, right? But unfortunately, right, score the award has to go to only one team, right? And based on the aggregate score, the winner team is Team 2 Drought, right? I think the lead for Team 2 Drought this year was Ethiopia. Congratulations, right? I'm again, right, for the other teams also, you did very well, right? And it was very close, right? But congratulations to on
Yes,
winning
you
for
guys
Team
were
2.
very close.
Yep.
Yeah, yeah.
I think,
Congratulations.
yep.
Great team. You did great job. Wonderful job. Wonderful job. All of you are winner for us. Um, you know, we, as I mentioned, as Dr. Bijoy mentioned, all of the weather, but you were really awesome, in the way 1 week time you could accomplish all of those kind of modeling, writing, presentation, running, cloud, age. It's wonderful. You got to be very proud of yourself. We are very proud of you and your accomplishment. Thank you very much for your contribution. And we encourage you guys to work on your position paper and enhance it and submit it to a peer review journal. We would be happy to help you if you decided to add additional analysis and analyze more kind of other kind of methods added to your paper. So we would be happy to help you as you move forward with enhancing this paper. Also, I don't know, Matt is here, Dr. Boyer. He said he sent email to you guys if you could answer his survey and also attend the interview and let us know what works well with you, what would be your recommendation for us to improve this program. That would be a great thing for us to enhance WaterSoftHack. So I would love to hear from you, your recommendation, your suggestions. And I understand it is a short time kind of research work. You have really 1 week to work and it is tense, but we appreciate all you guys done. You done really fantastic job. Thank you so much. Thank you very much. I am sure NSF is going to appreciate your effort and your contribution. And we will make sure to add some of your comment when we submit or report to the National Science Foundation, so they understand how our community think about the need of cyber infrastructure and the tool and cloud and edge computing that are essential for water science and engineering fields. And as Dr. Bijoy mentioned, each of you receive $1,000 from Clemson. So I will connect you with the Clemson business office. So you need to provide your address, your social security number, I guess, I don't know, to them. The process is just something they deal with. But yeah, they will reach out. You got to register your information. All will be confidential. You register on their system, and then they issue you a check to your address. Some of you who are international students, you may get some kind of cut in tax on something. We had some question last round too. These are something that they deal with IRS. So I don't know. It depends on your income and depends on your citizenship and all can change. So yeah, you will receive your honorarium for your hard work and your dedications, and we appreciate that a lot. Thank you very much. So if you guys have any questions or any suggestions, you can unmute yourself and talk and let us know what you like about the project and what would be your suggestion to improve and all.
I have a short question. We would like to submit the abstract to AGU. And what are the requirements? We're happy to add all WaterSoftHack peers as co-authors, but do you have any like recommendations on authorship?
Yes, you just need to select a proper session, Glena, and then the best fit to your abstract. What I typically suggest to my student is to submit like last 12-24 hours. I know there are some technical issue, but that time you're sure which session got more abstract, so you do not end up going with the merge sessions and all. So typically if a session get 24 or 26 abstract, the AGU assign them oral and poster session. So
Thank
you
you.
have better chance of getting oral presentations if you submit in that time frame to make sure that that session you're submitting, they get enough abstract. Otherwise, if they get less than 24 or 26, they merge session together and you don't know, you ended up getting poster or whatever. Oral is always more appreciated, right? So you have
But what
better
about
chance.
authors? I mean, we can add you, Bijaya, and Mikhail, and all of you as co-authors to this abstract, but I don't know if you need that. Like,
Yes, you can send us. I think we have a few days left before the deadline. We can review it, and then you guys can go ahead and submit it. I wish we had more money to support the AGU submission, and also I wish we had more money to give all of you as a winning team. But our budget and funding is limited by NSF. I pray that NSF get more money for water resources and fund water science related project more and more. But that's the situation we have. So yeah, you send us your abstract, then we'll be happy to provide some feedback, and then you submit
okay,
in
thank you.
appropriate session. Yes, great. So at UPI, you will get the 500 gift card. I think they send you some kind of code or something. I don't know. Clemson deal with it, business office, and you guys decide how you want to split among yourself. So you will get the $500 gift card. Okay. So as I mentioned, this was our last year of WaterSoftHack program. So we would really appreciate your feedback. If you guys could, fill out our survey, that we can reflect your opinion and your suggestion to NSF and say, hey, that's the need of our community, or that's what our community think about, having that kind of hackathon and training. So we appreciate your feedback. If you could provide it, that would be a great thing that help us to provide that data to NSF and also put it in our paper, which is under review currently. So we appreciate that. So any question you guys have, you can share any difficulty or any kind of challenges or any kind of opportunity you had during this program. I'd be happy to hear now.
I personally want to say thank you. This was really great. So it's the first time I learned about edge computing to understand how the sensors might be optimized this way and paired with the cloud. So it was really useful, expanding the horizons of the knowledge that I myself didn't have before. So thank you very much.
Great.
Thank you, Vidya. Vijaya, we learned a lot from you, and it was a great opportunity to learn about the cloud computing and edge computing. Hopefully, in the future, we will see again such courses, online webinar, and be able to collaborate with all of you in the future. Thank you all.
Yes, that's a wonderful job. Yes, you guys did really great. As I mentioned, all of you were our winner and very close. And it was really difficult for us to make final decisions. So that I think that was the longest meeting we had during these 3 years to decide which teams we give the prize. As I said, you were really, really very close. So congratulations. Congratulations, you did really great job. And thank you so much. So if you haven't deployed your project on WaterSoft Python package, Python repo, I would encourage you to do so that we can have your information and your project there. And it would be publicly available. So if you're willing to do that, and if you don't have any restriction in terms of sharing your data, your methodology, you can remove those confidential kind of data, but we would love to have your kind of project there so that next fellows or or water science community can use your kind of method, your data and your project and get some ideas. And truly appreciate that.
I'd like to second all the thank yous, and I think it was a very useful information how to combine this cloud and edge part. And I think I would like to say an extra thank you to Michael for organizing all this cloud part, because some of us were kind of new to the topic, and I think it was a very good and very detailed explanation. So thank you all.
Great.
Thank you as well.
Yeah, thank you, Glenn. And some of you guys are continued our program from the past year. We truly appreciate your interest and your support. Thank you very much. So, anything else, Bijaya? Ibrahim is here now? Okay, I will be in touch with you all regarding your check and how you can register yourself, your information in the Clemson system. Okay, look for my email. Make sure it is stick to your inbox, not junk mail. So thank you. Thank you all.
Yeah, thank you, everybody.
Yes,
so much.
have a
Thank
great
you.
day.
Bye.
Thank you. You take
Thank
care.
you.
Thank you.